Our next speaker is going to be Belfer from the Science, Technology and Society program in Bar-Ilan University. Israel's work illuminates the ways in which the growing importance of information and computation in science influence scientific thought. His works address both the history and philosophy of science in general and the history and philosophy of physics. Today we'll talk about, bit by bit, the role of information in physics.
Thank you very much. I want to thank the organizers and especially Oli for thinking of me and for building up exactly what I needed. In that case, I need to thank everybody because for me this entire workshop is a candy store because as you heard, the topic of my research is the way information influences the way we do science. Some of it has to do with the concepts that we heard about today, and some of it is just about what a science looks like when it uses concepts of information, and that's what I'm going to be talking about specifically now. The case study that I wanna go into is someone that we heard a little bit about beforehand from Daniel about Professor Yaakov Bekenstein, and to see how his implementation, his development of black hole thermodynamics with the use of informational tools influenced both the field but also physics in general, physicists in particular, and the way some fields in physics are being developed to this day. So just to make clear, what I'm going to try to do is, first I'm going to talk about a little bit biographically. The main thrust is going to be historical. There are going to be a lot of conceptual ramifications to the things that he does, but I'm not going to go deeply into them. I'm just going to point out things that correlate and correspond with things that we heard in the last couple of days, and I'm guessing we're still going to hear. And then towards the end, I'm going to look more into the kind of physics that is done inspired by him, sometimes directly encouraged and developed by students of his, and then what the kind of terminology that he gives us, how it's used in physics today. So Bekenstein, just the brass, like the small scale, the microstate of Bekenstein. He's Mexican-Israeli, but he moved through the States, so he was born in Mexico City, and then as a child he moves to New York. He's educated in the Polytechnic in New York. His thesis advisor was Krieger, and he told him that he should go to Princeton because that way you're going to stay away away from the lure of working on high energy particles or fundamental particles, because many people went that way and sunk. So in 1969 he goes to Princeton and he meets Wheeler. Of course there are things on the way. He finds out along the way with lots of broken glass that he's not going to be an experimentalist, Win. And then he talks to Wheeler about what he wants to do. And the thing about working under Wheeler at the time, anybody who met him or heard about the way he was working, he wanted everything to fit together in a way that was sometimes out of fashion, sometimes in fashion. He was around long enough to come in and out of fashion a few times. And at the time, what was called Wheeler's Boys, they were trying, each one in his own way, to work at something that Wheeler would see as a combination of quantum mechanics and gravity, something very, very ambitious. And the kind of ambitious project that he gave Yaakov Bekenstein, and as you saw before with the quote that Daniel gave us, he knew who he was dealing with. Yaakov doesn't need much. You give him a little bit of something, and their conversations, and both there are personal notes and letters that show that from both directions they both gave a lot to each other from these conversations. And what he gave Bekenstein as a project was basically look into black holes that were objects of, if you're thinking at the beginning of the end of the 60s, early 70s, objects that were dealt with very little. There were some people in England that were working on it, like Hawking, like Penrose, and some of Wheeler's students were working on it, but it's a subject that was first developed like half a century beforehand in World War II by Schwarzschild, and then there isn't a lot you can say about black holes, I think 1970s. And he thought that the lure of black holes, the reason why it's about time to reopen this black box, now that we have quantum field theory and things like that, is that there's a promise there, because it's a level of reality where both quantum mechanics and extreme gravitation occur together. They can't get away from each other. If there's going to be a fundamental law to physics, or there's going to be a fundamental behavior, because at some point they stopped talking about laws and started talking about behavior and law without law, it's going to be there. It's going to be on that scale. So he gives him black holes as a general project, but he also gives him specific things to look at, like the dynamics near black holes, which is stuff that Penrose was working on at the time. That is the area close to the event horizon of the black hole, called the ergosphere, where you could maybe try to extract work out of that extreme field. Maybe you can't, and that's the kind of work that Penrose was working on at the time. And there was one of the students of Wheeler's called Christodoulou, who's still active, and they discussed that kind of work, and that was the beginnings of the developments that he had. The non-conservation of Bar-Ilan number. When you get into the black holes, and this is where things started really rolling for Bekenstein as the kind of theory he was going to have to develop, because what he was seeing, whichever way he was attacking it, either through Gedanken experiments or through formal descriptions, what have you, or through phase space descriptions, fundamental attributes of the physical system seem to evanesce, seem to transcend when you get into black holes. Black holes can maybe spin, they can maybe have they can have angular momentum, the Kerr-Nordstrom black holes, and so on. They can have charge, but there are some very basic things about the systems that go into black holes that are simply inaccessible, utterly inaccessible. And this is something that was related, that was coined as the black holes have no hair theorem. Now, the review letters might have been open about publishing things that are practically available, but they were a little bit more stringent about things that sound naughty. So for a while there, you couldn't talk about black holes in the review letters because it sounded bad. And only later on, when it gained more authority, could you go back and talk about the no hair theorem. So the no hair basically tells us that nothing is accessible to us, but it's somewhere, if we need to conceptually place it, it's both epistemic and ontological. It's not that I can't see anything, it's that there's something there. If you take into account the evaporation of things like Bar-Ilan number, it's more than just what I don't know about the system. And this is something that, on the one hand, it seems a little bit like other systems that I don't know about their inner workings, and on the other hand, there's something more going on here. And the third was, and we heard about this also, the ever-increasing surface area, or coupled with mass, of a black hole. Some of the results of this were already around, and Bekenstein made some of these results concurrently. There was a workshop in the beginning of the 70s in Copenhagen that Bekenstein, and this is a lesson to all of us young researchers in the crowd, that Bekenstein was not accepted to. Even though he had results the same as Hawking's for some of the questions that were at hand, he was not accepted, and Wheeler told him, I can't do his accent. So Wheeler told him, just go. Get a ticket and go there. It's not a reason not to do science if you're not accepted into the conference. So he goes there and he finds out that, for example, the people from Hawking's circle are dealing with the same kinds of problems, and some of their solutions are similar to his, some of their solutions are different than his, but he couldn't get in, basically. I mean, he was left outside. He was working on his own. And one of the things that when I spoke with him a few years ago about this stage in his research is that he said, at this point, I'm not thinking explicitly about information. If I am bringing up information in my dissertation, it's because it was useful as a descriptive tool, and the metaphor he used was the horse and the carriage. At this point, if I bring up information, especially the committee that has to judge it, information is there in order to elucidate points. It's not there in order to describe things as these are informational objects and so on. So that's the horse pulling the carriage, where the carriage is classical physics. When I say classical physics, when I say classical physics, I mean physics that isn't imbued with informational context, that does not require information in order to make sense. And when I say now physics, it's physics that is very much information laden. So at this point, the questions are meat and potatoes physics. It's things that require solving, but they can't. I mean, there's a glass ceiling there. So some of the things that he uses are demons, as is customary in physics to use demons. So Maxwell's demon has been, and we've heard about this from different angles and a little bit at the time, in a staggered way. Maxwell's demon was a player in the analysis of inaccessible systems, or thermodynamic or mechanical, statistical mechanical systems since the end of the 19th century. Now, what Maxwell's demon does for Bekenstein, more than anything, is that it makes it clear that when you try to describe thermodynamic systems, the second law of thermodynamics is going to be inherently statistical, like we heard before, but very much statistical. Don't try to put it as something that is part of the system. But then he goes a different route than Oli does. And he says, and he chooses the route that, the same route that Einstein does, which is to say, well, this is the way the system behaves, and I'm going to assume that it's not for naught. It's behaving this way because the second law of thermodynamics is a principle that I should follow. Einstein goes even further than this. He sees the second law of thermodynamics as a call for him to find principle-based theories, and this is how, not how, but this is how he describes in his personal notes the drive to create general relativity and so on. If you have a principle, it's not something that you can reduce everything to, something that you can build up from. It's something that you put up as constraints on your system, or something that you require to be part of the furniture of the world, or part of the metric of the world, and then you go from there. So if you take the second law of thermodynamics and you assume it to be something fundamental, even though you don't know exactly what its mechanism is, because it manifests in a statistical way, but you're assuming that it's going to work in any system that you take, then Bekenstein tries to take the next step, which is to solve Wheeler's demon, which we heard about before. Now, what does Wheeler's demon do? It increases entropy because it mixes the hot and the cold tea, like we heard, and it pours it into the black holes, into the black hole. And at that point, and this is picking up exactly where you left off, because that was enough for Yaakov Bekenstein, because what Bekenstein realized is that some black hole physics is like thermodynamics, but some people had noticed that some of black hole physics is like thermodynamics, but Bekenstein insisted that black hole area is not just like entropy, it is entropy. And that was his reaction, not immediate reaction, but that was what he did with Wheeler's challenge. Now, when he says some people had noticed that some of black hole physics is like thermodynamics, is that at the same time we have from Hawking 3 or 4 laws of thermodynamics of black holes, but they're not laws of thermodynamics. They are very much insistently thermodynamics-like laws of black holes. And he gets at them through a description of what is the area and what is the corollary to the area and so on, but from very abstract, sometimes abstruse developments of field theory and things that I had a hard time following, and I had to work really hard at it. It works because talking's work, but it wasn't, and he didn't intend it to be an actual description of a thermodynamic system. Whereas Bekenstein, when he thinks about entropy falling into the black hole and what it has to do, he says, I need to assume that entropy is still growing. And then he starts connecting the dots. And I know about other things that are still growing in black holes. Some of them are growing. You know what? I think I'm gonna skip this because I don't have enough time. The common entropy in the black hole exterior plus the black hole entropy never decreases. Meaning there will be this attribute of the physical system which he's not really clear about what it is. In classical systems, it's statistical. But when you add that statistical entropy to this black hole, which you know nothing about, the result has to be more entropy. But then how do I describe entropy in this system that I cannot describe? But there is a description of this entity, which is the size, or the surface area. So there is an ever-growing property to the black holes, which is its surface area. And then there's this ever-growing property to the system, to systems in general, which is entropy. And then he makes the connection. And he makes the connection through another route, which is the same thing that Shannon knew about, which wasn't a big secret, which was the identity between, the formal mathematical identity between Boltzmann's H theorem and Shannon's definition of entropy in terms of information. But of course, that's not a definition, that's just a choice of words. And also, that's not what Bekenstein uses as a defense of his approach in his dissertation. This is something that he would publish, say, 10, 15 years afterwards. It becomes the staple, this homology, mathematical homology becomes the staple of a connection between information and thermodynamics, but that's not the way he started. That's something that was basically added on afterwards. Once you have a description of the system that works, say, in phase space, you can make a corollary of it in information and say, see, it's informational, even though you might claim that it's superfluous. But mathematical homology has always been a very powerful lure for physicists. If you see a mathematical similarity, you're assuming that there's something more to it than just the similarity itself, that there is a basic physical similarity. And also, as a technical side, when you have a system that you can't solve, you're always going to try to look at something that is solvable and maybe has the same mathematical shape. And if it works there, you're going to apply it. And if it's similar enough, at some point you're going to be talking about those two systems in similar ways. It doesn't mean that they're the same system, but this creates a context. So what he comes up with is that the entropy, the ever-growing property in thermodynamic systems, is transcended. There is a generalized form of it, which is the ever-growing property is now the ever-growing property of the surface area. And then there's this beautifully simple equation in terms of Planck lengths, which the Planck length is the unit that he was almost charged with using by Wheeler. And he said, if there's going to be a quantum gravity equation, it's going to be using Planck lengths. And it is actually a saturated case of the information bound, which means that the information of a system is always going to be smaller than the surface area times the mass energy, which is E. And it saturates when you go to the extreme of a black hole, which means there you have the highest degree of information. Now, recently, there was a memorial lecture celebrating Bekenstein's work, and Andy Strominger spoke about this, and he said that this simple equation is still considered one of the basic. It's on par with the basic formative equations in science today. But the more it is considered basic in physics, the more it's problematic, because the black hole, which is infinitely simple in the sense that it evaporates all the properties of the systems within it, is also the most saturated with information, which seems to denote some sort of complexity, and which is a problem that he tried to access. And he said that a lot of science will be coming in the next few years from trying to solve this kind of problem. So the generalized form of the second law means that you take mundane, day-to-day entropy, and you add to it the kind of entropy that you attribute to black holes, which you don't know what it is yet. You're just saying it in terms of its surface area. Now, this, in some ways, transcends the question of whether it is that I'm building thermodynamics on information or not, because the concept of entropy for black holes doesn't start off with me saying, well, there's some level of the system, and then there's another level of the system that I can or cannot. The entire system is describable in the same way. It is not describable. It is only describable in the sense that I do not know things about it. And this is where the epistemics of Bayesian statistics becomes almost ontological, because I do not know something about the system. The way he described it was, and this is also in one of the papers he described it this way, and in his last years this was the staple of the way he would say it. He would say, well, you have a series of protons or electrons or what have you falling in a series into a black hole, or becoming a black hole and condensing that way. So one by one you're losing information, because you know less and less about the universe, because one by one you know less. And this has, and then he says, this has nothing to do with the problem of, you know, the fate of information in black holes with a big war. You lose them one by one. And if you just quantify what happened mathematically, it is not just similar to Shannon's information equation. It is the same. It is that same thing. And there, it's not a mathematical similarity. It's a physical description. And the borders are thus really, you know, blurred. So that's the kind of work that he did in the beginning, and later it becomes something that becomes almost science fiction, but it's not. Meaning, in the beginning, it's about solving a system. You say you have infinite curvature and you want to know how you describe it, so you come up with something that belongs supposedly to a completely different word, like thermodynamics. What does thermodynamics have to do with curvature of space? But Hawking to the rescue, he does not agree with Bekenstein, and he doesn't like the work of the upstart, and still his work against him only vindicates, because it shows that black holes do exhibit some sort of thermodynamic behavior. But those who thought, like Wheeler, that there was something to what Bekenstein was doing, they didn't really require Hawking's vindication in the sense that black holes behave thermodynamically, maybe except to find that there's the 4 in the beginning here. Because in the beginning, they weren't really sure what was the number in the beginning. There was this, maybe it's somewhere between 2 and 6 or something. Because they were saying, I don't need thermodynamics now to behave the way it does in what I know in the laboratory. Thermodynamics is now something that's extended. The generalized form of thermodynamics is more similar to information theory, and this has nothing to do with justifying it. Conceptually, this is the way now some physicists try to do physics. Foremost, Wheeler, and we're going to get to him in a minute. Now, this kind of work is the later fruits of labor by Bekenstein and his collaborators. And I mean people like Gerard at Hooft and Leonard Susskind and Juan Maldacena, and people that worked on string theory and M theory, where the extension of information being entropy related to information, related to the surface area, begot some sort of, some would say, unholy connection where the information of a system is defined, the physical properties of a system are defined as the information that is encodable on its surface area. And then you start getting into surface areas of n-1 dimensions in an n-dimensional reality and so on. And this is the kind of work that's done in the late 80s and then the 90s. And there, information is already explicit. Information is already on the table. This is what we're looking for. We're using Bekenstein's work as inaugurating an information-based physics. Information is not just a metaphor or a tool to try to solve a system that is impervious to other tools. Information is now a bona fide physical aspect of the system, and an entire new field of holographic physics is born, where out of the work of around the circumference of systems and black holes, you're talking about the circumference of universes. You're talking about the circumference of entire systems of mundane plus black hole matter. It goes way beyond what Bekenstein did in the beginning, but at every point, it's still grounded on what he did, and he participates. Now, this is all, up until now, I was talking about what Bekenstein himself did or participated in doing. And of course, he started doing other stuff at the same time. This is only one aspect of a myriad of fields that he was involved with. He becomes part of the faculty of the young Ben Gurion University in the Negev, and later he joins the faculty at Hebrew University. And I was only talking about one aspect of the things that he did, but now I want to move a little bit to the influences. Now, one major influence that I see as an influence is the detractors, meaning someone who was against his work and ended up talking about information as something physical, which is, as far as I can, as far as I can see, historically, as the rise of a new kind of doing physics is a big win, is Hawking. Because Hawking starts off being the representative of classical physics. We don't need this kind of weird information thinking about black holes in order to solve them. And grudgingly, he finds that there is merit, or at least Bekenstein's description does not fall apart when you attack it. It actually produces results. And then afterwards, in 1983, in a series of conferences that included such people as Feynman and so on, and Susskind, he starts talking about the fate of information as it falls into black holes and what would happen to it afterwards. Does it thermalize, as in when the black hole evaporates, eventually the information is completely lost, or does the information in some way get woven into the fabric of the universe, or does not get lost? Meaning, in classical thermodynamic systems, information in its microstate does not get lost. It's there. It might not be accessible to us, but everything is there. But in black holes, this was the big question, and Leonard Susskind wrote about it in a very nice book called The Black Hole Wars. And my battle with Stephen Hawking to make the world safe for quantum mechanics. And then he goes into, this is Suskind's war, and he goes into attributing to Bekenstein the illumination of basic laws in physics, like saying information conservation is something so fundamental that it actually, if you read back to Newton, it's part of the way Newton does physics. That's the kind of influence that he sees Bekenstein having on science. This is actually Page winning a Marilyn Monroe dollar from Hawking after Hawking finally conceded in 2007. So information is safe. Now, I'm not going to get into all of this because I really don't have the time, but at the same time as everything else that I was talking about was going on, with holography and with information becoming part of the surface area of things, Bekenstein starts off what is later known as quantum information theory. But it does it quietly, and he doesn't go into the kind of work that we see with Holevo and with bounds and things like that. He starts analyzing information transfer capacity and the limitations that you might have with energy on these things. But this is work that influences his collaborators, and eventually this gets this becomes part of quantum information theory in general. But he actually starts it very early on. I mean, either the first one or one of the first people to deal with quantum systems as information transmission systems, and therefore requiring information theoretical treatment. Another influence that he has, and this is the last influence that I'm going to talk about, there are more, is his advisor himself, Wheeler. Now, Wheeler proclaimed about himself that he had three stages in his life. He had the everything is field stage, he had the everything is particles stage, and he had the everything is information stage. Now, Wheeler was around for so long that every stage for him was like an entire career for regular physicists. He was around almost the entire 20th century, since the 20s. He was Richard Feynman's advisor. And when he wants everything to be fields, he works at everything being field. And when he works at everything being particles, then he's going to, together with Feynman, show you that all electrons in the universe are the same electron. They're just traveling back and forth in time. He's going to make it clear. And when he gets to the point where everything is information, and he says it more than once, that this was influenced, not the least, by Bekenstein's work himself, he goes places where Bekenstein himself does not go. Whenever I asked him about it, he would say, well, it's an interesting idea, and I always thought it was very exciting, but because what he wants to do, as someone who has seen the glory days of quantum mechanics, but also their anxiety, he wants to take all the things that were problematic with quantum mechanics over the year, the observer problem, the spontaneous collapse of pure systems problem. All of these things, he wants to roll them up together and say that there's an informational aspect to it, which he coined the term "it from bit," where he claims that the ontology from information, and this information is at the same time epistemic and ontological, as you can see by the famous self-perpetuating circuit. Because when you view the universe, you are creating it, and so on. And I'm not sure what he would say about microsystems versus macro and preparing states, but there is a book, I'm almost sure that he deals with this, even in these terms themselves, called The Recursive Universe, where he takes in this kind of problem. He says, well, if you try to really make Wheeler's work reproduce everything we know about statistical mechanics and so on and other laws, does it really work? But Wheeler is an example of what I would call enthusiastic information physics. There are more extreme versions. There are versions like Fredkin's world as information structures. There are various versions of the world as a computational process. Some are extravagant, like Seth Lloyd taking off his shoe and saying, I can compute all of you with my shoe because it's a quantum mechanical flip-flop system. And then there are less abrasive versions of this that could pass for classical physics, like the work that Scott Aronson does, and we've heard about it more than once. And actually, Scott, when he came here, and this is now already 15 years ago, and he met Bekenstein as a grad student, and he met Bekenstein, and Bekenstein was the first one to tell him, oh yeah, I find it perfectly feasible that we live in a world that is a computational process. But he says this as a complete reductionist with a yarmulke on, which Scott found very cool. And so there's this difference between the advisor and the student, where Wheeler takes things very far, and Bekenstein was more careful. But the things that he inaugurates as a careful thinker, as a step-by-step results achieved and so on, give people like Wheeler the spark that they need to go much further than Bekenstein himself is willing to, or he's more careful about it. But towards the end, for example, in review articles that he wrote during the 2000s, there's one in 2005, there's one in 2009, Scientific American, New Scientist, about holographic universes and so on, where he says, well, it's perfectly possible that we are getting towards a physics, not maybe a physical reality, towards a physics that will describe reality instead of in terms of forces and particles or strings. It will be described in terms of an information structure or an information transference or an information processing. So in that sense, this brings me to the last part, where there is a new way of talking about physical systems, which is not just semantics. It's not just a jargon, in the sense that I can describe things that could have been described in a different way. I'm describing them as information, as an information processing. It's, even if I would say that they need to be described as information because for some reason they're reducible to an informational structure, or if I say no, information is just a convenient tool, is just a convenient choice of words because it's a shorthand for a lot of descriptive processes that I don't have the time for. Either way, this changes the way physics is done, which is what's of interest to me, because you can have projects like one that I just heard about from Sam now, because I knew about Hedrick. This is Matthew Hedrick from Brandeis, just as one example. There are many examples, whose work on connections between cosmology and quantum gravity and information have been going on for years, but now they've been coming up with translations of, instead of talking about information just in terms of bits placed on some sort of circumference ball like we saw before, which is a static description, and to some extent it doesn't really give us the dynamic of the system itself. They start talking about flows, and they bring in tools from network theory about min-max flow, and they can both allow for the specific mathematics of information theoretical terms like mutual information and so on, and explain curvature and emergence of properties in space. And these two topics, they have been, the way Strominger put it, they have been a promise that were given by Bekenstein some 40 years ago, 45 years ago, and now they're starting to get cashed out, I mean, at least physically. The philosophers are going to have to deal with the problem of why they're using these concepts so haphazardly and so free-handedly, but that's the way physics is directed, or directions that it's going these days, thanks to Bekenstein. Thank you very much.
So I think that for many people in the room, including me, Yaakov Bekenstein was an admired and beloved teacher. So thank you very much for this talk and for bringing me back in mind. Let's open the stage for discussion.
So I couldn't tell whether you were endorsing this informational term or just describing it, but
I kept on telling myself I don't have an opinion. I don't have an opinion. I don't have an opinion. I mean, it's problematic if I try to put my own thoughts into it. This is more historical.
I mean, I was just wondering if you could describe or just say a little bit more about what we gain by talking about information rather than entropy, or rather than using the non-informational language to, to describe these things. It seems like this is just so in confusion in exactly the unfortunate way that Willy Schenker described earlier with von Neumann's
first of all,
suggestion.
in cases like black hole physics, there's this black ceiling. There's this glass ceiling that you need to think outside the box for. And in that sense, talking about information as a one-off, let's say that's permissible even to the strict teacher. I used it in order to get away from a problem I couldn't solve, and that's what he did as a PhD student. But what you're asking is the generalized form. And there, what I'm going to say is, I'm not going to justify it philosophically. I'm going to say something that's more semantic, something that has to do with the kind of research that's done by Ian Hacking, Toronto, where he talks about styles of reasoning. When you have a new way of talking about things, when you have a new set of vocabularies and a new object that you can describe, you can formulate questions about them that you couldn't formulate before. You can try to find answers. You can try to look for dynamics where you didn't look for them before. The most famous example is statistics in general. Like when it rises in the 19th century, it changes the way we talk about reality, about human reality, about physical reality. And it's not that we couldn't try to describe it differently. It's that it changes the kinds of questions that we ask, which is a huge gain in and of its own. He also goes further and he says that you're going to have new objects. You're going to have a new reality. There's going to be a new feel to reality. But even if you don't accept that, it changes the way you do science.
I mean, okay, so yeah, obviously it increases lots of options, but is it really good if it opens a lot of misleading options?
I tend to think, and this is influenced by my teacher, Sam Schweber, I think of science the way I think about reality in very evolutionary genealogical terms. We need to take as many wrong turns as we can.
Yeah, thank you very much for a really terrific talk, really helpful. I was wondering if you could help me with explaining some stuff on the idea of the physical foundations are ultimately informational. So you mentioned the holographic principle and the idea that all of the physical properties of the system can emerge from informational states on the boundary of the system. So whenever you're talking about information, whenever you're attributing information to a system, you're really attributing probabilities to that system. Okay, so information is just a function of the probabilities. So I just wondered if you could say a little bit about how you would answer the questions that Orly asked earlier in her talk. So if the foundations are informational, what are the probabilities of, and what fixes those probabilities? Where do they come from?
Okay, so just as tradition of science, say that we need a basis, some measure. It's accepted as a need in order to do the calculation, but you have from Empedocles to Peirce, you have systems that do not require a measure as a starting point. Empedocles had it easy; he could just claim it. But what I'm saying is that the one side, this is a two-part answer. One side of saying yes, information. If I describe it very almost childlike in that picture, as saying, yeah, we've got bits encoded on the surface area of your system, so you're good. I mean, you don't have to worry because everything's there, and you're not actually here. But you're saying, but what does that mean? That just means that there's a statistical thing there. That doesn't really change the situation from a classical system where all the statistical occurrences were here. If I think that the world is inherently statistical, down, all the way down, then it doesn't really matter for me if I do it here or do it there. The question is, what do I gain by doing it there? Is there something, do I gain, for the string physicists, do I gain a fundamental theory that I can now use that will be more internally consistent and so on? That's the drive for them. But work that's being done now is asking the exact same question that you're asking. And they're saying, well, but they're framing it a little differently. They're saying, well, this doesn't give me a full account of information theoretical behavior. It's just claiming that it's information, whereas the the actual mathematics of information theory, and then the other hand, what does it do for me physically? And that's exactly the kind of questions that are being answered now. Because up until now, when people would discuss holographic approaches, it would be enough for them that it describes an internally consistent set of dimensions, which was what was needed for that kind of theory. But once that's done, since, I don't know, 97, 98, the work of Malacena, of course your question becomes the pertinent one, and then that's exactly what they're trying to answer now. But they're trying to do it with physics. I mean, not with conceptually saying whether it's permitted to talk about that part of the world as statistical versus another part. I don't know.
Yeah, no, that's really helpful. That, you know, on the one hand, you might just find a mapping between your physical theory and some information theoretic account. Great, but then how do you interpret the information theoretic account? How do you interpret
and then I was about to say, and then there are I wouldn't say they're running away, but then there's the complementary side of looking at information processing. And information theoretic and information processing, I belong to the school of thought that the things that they are related in a fundamental way, but still, when a physicist is required to talk about the system, and he says, up until at one point he speaks Shannon speak, and then not Shannon himself, Shannon was very diffident about this, and then at some point he starts talking Church Turing speak, and then he doesn't, and he does it seamlessly, he or she, I mean, and that seems like an escape. But for them, as long as it meshes together and it gives a complete picture, for the physicist it wouldn't matter. I mean, I'm not really required to go all the way and for the entire world to be just information theoretical, because, and this has been commented on, in the thermodynamic, in the statistical mechanics sense, if you try to equate information theory to thermodynamics, information theory does not have a trajectory in the formal sense of the word, in a thermodynamic phase-based kind of, and so it's limited anyway. I mean, it's just a starting point that makes you think that information might have something foundational to give you, and it gives you a series of things, but it doesn't give you the entire gamut of physical laws or behavior of that system. And people are hoping that it might be hidden there somewhere, and once we approach it from a different angle, we're going to find it. So that's where things are right now.
You may want to reject my question, but it's inspired partly by that picture and what Mark said.
This picture?
Yes. And I want to bring up topology, which hasn't been mentioned, and there's a hole.
Yeah.
And one of the things that I've been deeply impressed by is that a lot of what has come out of mathematics since Euclid and before is not expressible in terms of probabilities and numbers, but has to do with continuity and continuous deformability and what is possible and impossible as opposed to more or less likely or probable.
Yeah.
So for example, on a plane surface, if you have any two simple closed curves, non-self-crossing, they can be continuously deformed into each other. Likewise on a sphere. But as soon as you add a hole, you can have, and I leave this as an exercise for people who never met this before, several classes of continuously, of closed simple curves, which are not mutually deformable continuously. And the question is, how many classes can you think of in the next 24 hours or so if you've never thought about this before? So there's something there.
I gave this to my kid. He's not talking to me yet.
Sorry?
I gave this to my kid a few weeks ago as a riddle, and he's not talking to me.
Okay. Anyway, we can talk more about your kid, because I think kids has an awful lot to teach us, even before they start using language. But, so my question then is, if space is important and continuity is a feature of space and impossibilities and possibilities as opposed to probabilities of features of spatial structures, is it possible that there's something about chemistry that makes use of properties of space? For instance, there are things that fold and unfold, and topological changes occur when bonds form or are released. Is that left out of the physics that treats everything in terms of numerical values that change? You know, some collection of measures, which a fixed number of measures, however large they are, even if they're infinite, there's something that doesn't seem to be capable of capturing these geometrical, topological transformations, which may be constraints in the physical world that we need to understand. So information, maybe information about what's possible or impossible, and some physical changes may change what's possible or impossible. Well, we know that when we make skyscrapers and car tires and all kinds. Does that make sense?
Yeah, of course. And the big problem is that the people who might develop very usable tools for this, they belong to, you know, astrophysics or abstract mathematical physics, but the people that do biophysics might not they might not be talking to each other.
I heard a talk a couple of weeks ago about Dana Scott on how to get geometry without starting from points. Some people may know that. It's available online as a lecture he gave a couple of years ago.
Oh.
Thank you for a really beautiful talk. I want to bring you back to Bekenstein on a personal, that is on a biographical personal matter. It's well known that Einstein really hated the idea of a black hole, and partly because of contingency. Black holes come out of stars, which they're different kinds. Did you ever hear any comments on that issue from Bekenstein?
No.
From what you say, and other things I've read about this it from bit idea, there seems to be a weaker version or a weaker way of understanding this, which is just that it's a different language, it's a different way of thinking about the physical world. It can give you interesting results, and there's nothing ontologically problematic about that. But there is this stronger way to think about it or to construe it, and I think there's a word in there that suggests that. No. Immaterial, an immaterial source. So immaterial, at least to my philosophical ear, suggests that we're positing some kind of basic ontology that is not that is very different from the concrete physical world that we're normally observing and trying to explain. And you know, other things that I've read are hardware is made of software, or the use of the word abstract, that this is an abstract entity that is at the basis of the physical world. And to philosophers' ears, again, abstract suggests something that you know, an abstract entity is supposed to be non-spatial, non-temporal, and non-causal. So if that's stronger,
as Olympia said, it's got to be manipulating and it's got to be influential. But how does it do it?
Right. So how can you recover the concrete aspects of the physical world, the spatio-temporal causal aspects, if you're positing this immaterial or abstract kind of thing at its bottom? Yeah. So do you have any thoughts about that?
First of all, he couldn't. I mean, and I always thought that that was part of the reason why, with all of his enthusiasm and personal charm and the way he could bring people around him to Texas to do work, eventually it was, I wouldn't call it a dead end in the sense of a wrong conclusion that would come out of that school, but it didn't really produce the kind of big scale physics that he wanted. And the reason, at some point, I decided or got to the conclusion that it was because of this thing lying in the background, where the material comes from the immaterial, and for a physicist that might not be the age to talk about it. There was an age where you could say it, but today it's a problem. No, but he could also talk to you about law without law, and Sam can talk about it way better than I could. But so that's the kind of frame of mind that you would get from Wheeler. But you're right that we are breaking, and I'll phrase it this way: the kind of fingernail on the board screech that the philosopher hears here is that, first of all, information is supposed to be embodied on something, and you're talking about it without embodiment. And the other thing is you're talking about embodiment coming out of information. What the hell is that about? I mean, how does that work? Now, the physicist jumps over that hurdle and says, but what does it do for me? And then after he says that it can do things for me, it will retroactively, redeem itself. Come with me, build it with me, and then they will come, or the other way around. Yeah. But philosophically, you're absolutely correct. There's either some reason to break everything down or something to answer. But I don't have the wherewithal philosophically to answer that question. I can only agree that it's a deal breaker.
Okay, we'll have a 15 minutes break, and then the other